Thank you for the invitation. I'm going to discuss a novel approach to QCD color confinement and Hadron spectroscopy. And it's based, in fact, a lot on the quark-diquark model that we've been discussing. It also comes from light front holography. This is the connection to higher dimension of space-time. That's over here. And also, I always put this slide up here to show that the proton is very complex. It's got C quarks and so on. A complete treatment is really very complicated. And this is sort of a list of all the collaborators I've worked on with this light front holography approach. So the proton is actually, as you'll see, a quark-diquark structure, and you'll see how that works. The first starting point is that this paper by Klimt and Mesh, where they showed the remarkable fact that the Reggie trajectory for the deltas is the same as the Reggie trajectory for the rho omega, at least the slope. They're very similar. And how it's possible is really remarkable because the mesons are quark-antiquark, the baryons are three-quark systems. How can they have such similar dynamics? And also, it's not just in J, but also in L, and they have the same slope. So I'm going to show you in this new approach called supersymmetric light front holography, the rho and delta trajectories are actually right on top of each other. And here's the rho trajectory, and here's the delta trajectory. And I'll show you, in fact, that virtually every hadronic system has this remarkable supersymmetry between the mesons and the baryons. You'll see how this emerges, the same slope, not just in L, but also in N. The mesons are quark-antiquark, and the baryons are three quarks, but actually they're quark-diquark states. And so we're really equating fermions and bosons. So we really have a supersymmetric structure right in front of us where we're relating mesons and baryons. But there is a point that actually, when you do the plot, the meson angular momentum is 1 unit higher than the baryons. So you'll see how that works. So this is supersymmetric QCD spectroscopy. And one of the ways to understand it very simply is this plot right here. The meson is quark-antiquark. And then when you apply a supersymmetric operator, the 3 bar, the antiquark, becomes a diquark. And that becomes the baryon. But there's actually 2 states with L and L+1 that emerges naturally out of supersymmetry. And then when you apply the supersymmetric operator one more time, it takes the quark in the diquark system into a diquark, diquark system. And that gives us the tetraquarks. So you actually have the same spectroscopy, not just for the mesons, but for the baryons and the tetraquarks. So this operator R is taking the antiquark from the diquark. So that's really important. So and we're always, of course, conserving color. The 3 bar goes to the 3 bar. So the proton actually then is a U quark with a UD diquark, and it's a quark with a scalar diquark. And it turns out remarkably that in the massless quark limit, you actually have equal weight between the L = 0 and L = 1 baryon. That's pretty remarkable. So we're really going to talk about now approach to color confinement, origin of the QCD mass scale, the meson and baryon spectroscopy, exotic states like the tetraquarks, universal Reggie slopes. The pion turns out to be massless in this approximation for 0 mass quarks. It also gives us the QCD coupling at all scales, and I won't be able to talk about it here, but we can eliminate scale uncertainties and scheme dependence from the predictions. And what we're also important point that we can start with Lagrangian of QCD and derive the light front wave functions, which control all the observables that we measure in experiment, both the valence and the higher Fock states. So what we really need is a first approximation of QCD, which is comparable in simplicity to the Schrödinger theory in atomic physics that Chris Quigg beautifully discussed today. And we want a formalism which is relativistic, but not only relativistic, independent of the observer's frame. You really want Poincare invariance, color confining, and so on. You want to understand the origin of the hadronic mass scale. So this approach called ADS-QCD, light front holography, and superconformal algebra does all that. And the only parameters actually is, in fact, the quark masses. So going back a little bit, I think most of you know, in fact, there's the light front formalism where, in fact, you quantize not at ordinary time, that's Dirac's front form, and you quantize a fixed light front time. And the advantage of this is that everything is invariant under boost. Nothing depends on the observer's frame. The wave functions that you get are independent of the momentum of the hadron. And you get simple equations, Heisenberg equations, where the eigenvalues are m squared. And this, every hadron then has an m squared. And the light front wave functions are then tell you the underlying structure of the hadrons. So we're looking again to fix light front time, not ordinary time. And the familiar to you is if you start with a hadron with momentum p plus, p0 plus p3, and p perp, you can decompose it in terms of its quarks, xp perp, xp plus, xp perp, and k perp, and so on. So the hadron eigenstate, when you expand it, starts with a proton with 3 quarks, and then has all the higher Fox states. So there's no approximations. This is the light front Hamiltonian formalism, and the eigenvalues of the light front Hamiltonian give the masses of all the hadrons. Again, fixed light front time. The sum of the x's is 1, the sum of the k perps is 0. Everything's invariant under boost, independent of the momentum. So and the formalism is causal, frame independent, accretion operators on a simple vacuum. Current matrix elements are overlaps of light front wave functions. And if you just do dipole axis scattering, then like the famous Bjarkane slack experiment, then in fact you identify the x of the struck quark, the light front fraction, momentum fraction, that's k plus over p plus, with the Bjarkane variable. So it's really like taking a flash photograph. So also when you know the light front wave functions, you as Larset and Pasquini showed, you really are in fact showing, allowing you to predict all the different experimental variables and so on that we know and love. And you also derive the evolution equations and so on, factorization theorems from this formalism. And if you do form factors, for example, you're just taking the overlap of the light front wave functions, you choose a frame Q plus to go 0, so the photon doesn't make pairs, and then it just tags the quark with momentum x and k perp, changes to x and k perp plus q perp. And so if you know the light front wave functions, you compute the overlap of the light front wave functions, and that gives you the Drell-Yan-West formula, exact formula for the form factors. Now, so measurements are made to fix light front time. Causality is automatic. Structure functions are squares of light front wave functions. Form factors are overlaps and so on, and so on. It goes on and on. And light front wave, turns out light front holography is actually an amazing fact that light front physics in our world, 3+1, is dual to anti-de Sitter space. So go on. I'm going to skip some slides because of times. There's no pancakes in this formalism. There's no boost to do. Everything is frame independent. Now, how do you derive this? You start with Lagrangian and QCD. You use the standard methods to get the Hamiltonian. The Hamiltonian in light front, instead of p squared over 2m, it has this kinetic energy operator, m squared plus k perp square x, plus all the interactions. So in QCD, we know all the interactions. They're very simple. You have the 3-gluon, 4-gluon interactions, all the other interactions. There's no ghost if you choose what's called light front gauge. And then the eigenvalue problem is h psi is equals m squared psi, and then you expand the hadron eigensolution on the free Fox states, and that gives you the light front wave functions. And so the eigenvalues and eigensolutions give you the whole spectrum and the light front wave functions. So actually, there's a method by Hornbostel, Paul, and myself, DLCQ, we can actually diagonalize the light front Hamiltonian on a matrix. So I won't go through this, but it's really a very elegant way to solve quantum field theories. And you can also do perturbation theory very simply with this formalism. I'll skip that. Now, if you start with, again, with the light front Lagrangian, you derive the light front Hamiltonian, you get the free term plus the interaction terms. We know what they all are in QCD. And this gives you, in fact, coupled Fox states. And the eigenvalue of this equation is the hadron mass spectrum. Now, in fact, for the 2-particle case, you get just k perp squared plus m squared over x1 plus x equal mass quarks, and then a potential, which comes from all the interactions, and then this equation. This is a light front Schrödinger equation. So it's an exact equation, works in any simple system. And what happens though is you can write this equation in terms of, let's put the quark mass to 0 in terms of a simple variable d by z zeta squared. It's like a radial variable. And then there's an angular momentum term that comes from this term, and then the potential term. So this is actually a basic, again, light front Schrödinger equation, which is very simple for physics. And anti-de Sitter space, QCD, actually tells you, in fact, what this potential is. It's kappa to the fourth, that's the basic mass scale, plus the terms involving the internal orbital momentum and spin. And here zeta squared is just the b perp squared, the transverse distance between the quark and antiquark times x1 minus x. It's actually a three-dimensional object, which is frame independent and rotational invariant. So this is really a beautiful, simple system. Now, what's amazing about this ADS QCD, it tells you the potential for QCD, and it's actually a confining potential. It actually grows with zeta squared, the distance between the quarks, and it has the correct spin dependence. So in fact, this is really, if you like, a semi-classical first approximation to QCD, which is really remarkable because it basically accounts for the whole hadronic spectrum, and it's got confinement built in as well. So this model uses this three-dimensional zeta squared variable that's crucial between a quark and antiquark, and you get this beautiful light front Schrödinger equation, and there's only one mass scale kappa, and once you set kappa by one observable, you have it for every other hadron as well. So an origin of this thing is actually conformal symmetry of the action. One way you can understand this is actually you start with a theory which has got conformal invariance, and then you introduce interactions which retain the conformal symmetry of the action. You actually get this equation. So that's one of the principles. Another principle comes from fifth dimensional ADS space, where you have what you call is a dilaton, and that becomes e to the plus kappa squared z squared. This soft wall model for the dilaton is what generates this very simple term. So d'Alpha, Fabini, and Furlan, they showed how, in fact, the scale can appear in a Hamiltonian equation motion without affecting the conformal invariance of the action. It's rather remarkable fact. And so this model is really based on this principle of d'Alpha, Fabini, Furlan, and Rabinowitz. Now, and again, only ratios of mass are determined because the GeV units are external to QCD. So it would take for a long time to go through all the analysis in the fifth or higher dimensions and so on, but there is an extra fifth dimension in ADS space, and this is the free term, the conformal term. I'll have to go through this quickly, but what you do is then you actually see this as actually a fifth dimensional representation of quantum field theory, and as you go out in this distance z, it's like you have confinement in that direction. So what happens is that you introduce what's called the dilaton, which conserves the conformal invariance of the theory, but it actually has then this extra e to the 5z. And this is actually then the ansatz for how you do this thing. If you choose this beautiful dilaton, which has all the right features, it introduces this mass scale kappa, which is actually the confinement scale. And you actually have then confinement potential in the fifth dimension, which actually gives you all the right physics. This is also related to work by Klebanov and Maldacena in ADS 10. Now, when you look at this light front Schrödinger equation, what you have is in fact two terms: kappa to the fourth zeta squared z squared, which this is in the fifth dimension, and that with this extra terms. And then when you translate that with the fact that z and zeta are actually identical holographic duals, then in fact you get the equation for 3+1 physics, and that's light front holography. So there's a duality between the wave function for a two-particle system in the fifth dimension with variable z and the light front wave function here. If you know this one, you know this one. If you know z, you know zeta, and you have this beautiful then relationship. And you also have solutions then between the light front wave functions in our world and the light front wave functions in the fifth dimension. And this light front holography really is derived, in fact, because you can actually notice that there's an equality between the Drell-Yan-West formula for form factors, not only electromagnetic, but also gravitational form factors, and the ADS space when you make this identification. So you take the Polchinski-Strasser formula in the fifth dimension, and you get our world by just making this identification. So I'll just say a couple of words about it. You take the Soper formula, which is the Jolyon-West formula in coordinate space, and you introduce this variable zeta, and you get exactly the Polchinski-Strasser convolution formula. So that's really one of the main connections between these formalisms. So you use this dilaton, e to the plus kappa squared z squared, you get this equation, and then you get these, you get two things which are very important. You get the light front wave functions for every two-body system, and you get the mass formula. So this is like the Bohr spectrum. You get 4 kappa squared as the mass square scale, and then it depends on n, the principal quantum number, and the orbital momentum and spin of the system. Really elegant formula. And it really works. And so I'll review this. Now, in fact, one of the things that's very interesting, in the case of the pion, you actually get 0 mass for 0 quark mass, because n is 0 and J and L are 0. And the reason why this happens is that in the light front potential, you have the confining potential, but you have this J minus 1 term, and the J minus 1 is negative. So you actually get a minus 2 kappa squared, and that's what makes the pion massless. So the same formulas work for the pion as the other hadrons. So you get the light front wave functions in Z or zeta. You get this is as you go up in L, this as you get nodes as you go up in N. You get the spectrum of the pion, which has got 0 mass in the 0 quark mass limit, and you get its excitation of the pions both L and N. So the pion has 0 mass and the same slope in N and L. There's only one mass parameter. And then you go ahead and you can do the other trajectories. You can do the kaon trajectories. You introduce, of course, a mass for each of the quark masses, and then you get the spectroscopy of the hadrons. And all comes from this elegant formula, 4 kappa squared n plus L plus spin over 2. And with, again, equal slope in N and L. And then also, there's the tetraquarks. And we'll come back to this, but the tetraquarks come from the same supersymmetric operation that we discussed before. That is, if the antiquark in the meson becomes a diquark. And then you get not only the meson baryons, but the tetraquark spectrum as well. So you get, here's again the Regis trajectories, and here the way the masses come in, it's just simply the expectation values of the m squared over 1 minus x. So you have a relativistic quantum mechanical wave functions. Nothing depends on the observer's motion. There's no Lorentz contraction, and you get these light front wave functions. And for the valence wave functions, it's very simple. You just get the beautiful light front wave functions, and they look like this. They're Gaussian shape. They have a form e to the minus kappa squared, k perp squared over x minus x. This is actually invariant mass of the quark antiquark, and then the prefactor, which is automatic. And when you calculate the distribution amplitude, which is the integral of this thing over k perp squared, then you in fact get a simple form for the pion distribution amplitude, just root x1 minus x. And other people have actually derived this independently from the Dyson-Schwinger equation approach. So you actually get this same type of answers. But now what we really have is a connection of confinement to the hadron structure, because this whole formalism is color confining. And so we have these light front wave functions, and really, in fact, we can take a quark and antiquark and make a meson. And that's, in fact, hadronization at the amplitude level with, in fact, color confinement. So when you calculate the pion form factor from the Jolyon-West formula, it looks very close to the data. And you can even do time-like pion form factor as well, with the extra contributions and the extra pole structure come in this analytic form like this. And then you can check this thing in diffractive row production, for example. This has been done by Forshaw and Sanapan, and you find out that the data is perfect with this Gaussian wave function that comes out of ADS5. And then you also get structure functions, also polarized and unpolarized structure functions. So you get the whole spectrum of light front wave functions of the hadrons, and that's, for example, the G, and you see how it's peaked at where the heavy quark carries most of the X, which is just kinematics. And so going back now to these theories, you can actually now go back and introduce supersymmetry. And what happens, first of all, is you start with this equation for the light front Schrödinger equation and for the mesons. And I should say right away, in fact, if you go to the heavy quark limit for that equation, it immediately gives you the linear term, the famous sigma R term for the heavy quark system. So you reproduce, in fact, the formulas for heavy quarkonium from the same light front potential. So everything is relativistic, frame independent. The QCD mass scale appears as a unique light front potential. You reproduce the spectroscopy dynamics of the light quark hadrons. You get the zero mass pion for the zero quark mass, the same Reggie slopes in N and L. You get the splitting in L persists to high. It's really linear trajectories. There's no, and you get phenomenology, light front wave functions, form factors, like productions, and so on, all from this one potential. So if you start with a QCD Lagrangian, basically the chiral limit is you set the quark masses to zero. So where does the QCD mass scale come? You don't, QCD does not know what MEV units, so only the ratio masses are determined. And that's all that we do. And then the scale can appear in the Hamiltonian without affecting the conformal invariance of the action. It's a basic principle. And that's what this whole formalism obeys. And that leads to this unique confinement potential. So let me say then, in fact, with the same procedure, then we can go for the mesons to the baryons and the tetraquarks. Now, when you introduce supersymmetry, you start with superconformal quantum mechanics, Haag et al. And then it has these equations, you generate this conformal algebra, and so on. Basically, you find that you're looking at the square of the Hamiltonian, and the square root of the special conformal operator is the crucial dynamical variables. And when you go through, I won't take time to do this, when you go through supersymmetry, you get these beautiful equations which relate the each term in the equation. But the most important thing for us is you start out with the meson equation, which we discussed before, which comes from light front holography. And now when you apply the supersymmetry, you get the baryon equations. You get an equation which is really two components, the upper components, if you like, of the Dirac spinner, the upper two components and the lower ones, they both obey the same spectrum and so on, but you get equation for both the upper and the lower component. And you find out that in the massless quark limit, you get equality between the upper and lower. So you have equal weight for the proton with L equals 1 and L equals 0. So you get, and again, so you get this meson baryon degeneracy. Also, the form is, if you look at the eigensolutions, the meson solution, the baryon solutions are identical, except that there's an extra +1 in the baryon solution. So that's so that you actually get this meson baryon degeneracy when you relate Lm, the meson orbital momentum, to the baryon orbital momentum and add 1. So we know the light front wave functions for the baryons. They look like this in terms of the variable zeta. This equal probability for the upper and lower components. You get and the eigenvalues and so on. And so then you get the beautiful wave functions of the hadron, the baryons. And so when you do this, you get the whole spectroscopy of the baryon spectrum. You get all the Reggie trajectories. You get the fact, you get the same slope between the pion trajectory and the nucleon trajectory. Again, you have to add 1 unit of orbital momentum between the mesons and the baryons. So the mesons have 1 unit more of orbital momentum between the quark and antiquark versus quark and diquark. So you get universal slopes in N and L, and you get this beautiful formulas for Reggie type formulas for the mass spectrum. And here's another example. This is, I showed this at the beginning, the rho trajectory, the delta trajectory are basically degenerate. Mesons and baryons, that's supersymmetry. You also see that every Reggie trajectory gives you the same slope. We actually introduce sometimes instead of kappa, we call that square root of lambda. Lambda squared is kappa, lambda is kappa squared, and that's 1 number in GeV units. And then you have 1 universal mass for the quark masses, for the mesons and for the light quarks and for the heavy strange quark. So again, what we're doing is we're taking the mesons, which are quark, antiquark, applying the supersymmetric operator that gives us baryon bound states in terms of the quark and diquark with equal weight between the L and L+1. And then the tetraquarks, again, are the diquark, anti-diquark. So this predicts the whole spectroscopy of the mesons, baryons, and tetraquarks with 1 formula. And it's all based on this one operation that the Q bar in the meson becomes the diquark in the baryon, and so on. And so here's also an example where you have the F2 trajectory, the delta trajectory, and the corresponding tetraquark. And you can go through the whole hadronic spectrum. Marina Nilsson's the hero on this. She went through the whole spectrum and identified how you actually identify the QQ bar, the diquark quark baryons, and the diquark antidiquark tetraquark together, and so on. So there's a universal mass formula for all the hadrons in terms of N and L and their spin contributions. And you get a universal light front kinetic energy and light front potential energy, a Viral theorem, and the universal constant from the spin terms. And then you, again, for the proton form factor, you get pretty good results. These things based in the counting rules, they're all based in. In fact, you don't have to add them in. They're all right from the beginning. The only thing that doesn't work too well is the neutron form factor in this domain. Aside from that, you get the Pauli and Dirac form factors really quite well. And here's again the Pauli form factor for the proton. And you also get the quark distributions. Here's trajectories for the strange quarks. The meson and baryon trajectories are degenerate. Then you have the degeneracy in the charm quark sector between the D spectrum system and the lambda C baryon spectrum. And you go through, in fact, and you can find again the meson, baryon, and tetraquark degeneracies that you'd love to have. And here's again more of these examples of the supersymmetry across the light and heavy quark system. So even the heavy bottom quark does not break the supersymmetry. And then we can also apply this to the charmonium states and the corresponding tetraquarks. So really what we're talking about is the supersymmetry is a hidden supersymmetry, symmetry of color SU3 color in hadron physics. There's no squarks or no gluinos. It's just an algebraic identity. It emerges from light front holography and superconformal algebra. You have color confinement and, amazingly, a massless pine in the chiral limit. And it's all based on this one picture then of meson, baryon, and tetraquark by this one simple relationship with our lambda, our delta. Okay. You can also find hexaquarks in nuclei. In fact, you can explain why, in fact, the alpha particle has such anomalous binding energy and so on. So we're using Poincare invariance, independence of the observer's Lorentz frame, causality, light front holography is this amazing identity between Z in the fifth dimension and zeta in our world, where zeta is just is a B perp squared x minus x, which is conjugate of K perp squared x minus x invariant mass. You're introducing a single mass scale while returning the conformal invariance to the action. You have a unique dilaton in the fifth dimension and a unique color confinement potential in our world. And you have this, again, relation between superconformal algebra, between mesons, baryons, and tetraquarks, a mass degenerate fourplet. And other things you can do, you can actually derive the other features of the mesons, the valence, quark distributions, and so on. Also important thing is you can see the size of the hadron, the transverse size, the invariant size, as you go to x equals 1, becomes point-like. So that's the origin of color transparency, actually. So I've shown this before in different slides and so on. These are the polarized and antipolarized predictions. You get the right answers. You also can understand you have confinement in the transverse direction, but you can also understand now, if you introduce quark masses and so on, how you get, in fact, the confinement in all three directions. And there's a lot of work on this. This is just one example by Chevchevska and Hiller, where you actually have then equations for both the transverse thing, which I showed before, and then an extra term from longitudinal confinements, which comes from the finite quark masses. But you retain
Stanley?
Again, it's that. Okay,
Stanley,
so I
please.
should stop.
Could you
I
go
will
to the
stop.
conclusion?
Okay, let me see.
Could you please go to the conclusion? Sorry.
Okay, certainly. I'm sorry. I get out of control. You can actually derive the Gell-Mann-Oakes random formula from this formalism. You have condensates, which are not vacuum condensates, but in hadron condensates, and so on. And I want to show you one more thing, which is what also comes out of this formalism is actually work we did with Alexander Duhr, Guy de Terman, is the running coupling at all scales. So in fact, the running coupling of QCD is predicted to be a Gaussian at low Q squared. And this is you have a Gaussian at this low domain, at a point Q0, it actually matches the perturbative QCD expression. So you actually have a transition between non-perturbative perturbative QCD, and you get beautiful agreement between experiment and theory with the same parameter kappa that we had before. And so it's really, in fact, a remarkable thing that we now have a starting point for decapitable evolution, and we have, in fact, a Gaussian shape for the running coupling. And you could use the Bjorkane sum rule to actually determine this alpha of Q squared and low Q squared. You use the data, and you get, in fact, beautiful fits to the running coupling from this asymptotically flat domain to the perturbative domain, and all with one, in fact, simple analytic formulation. And this leads to this color transparency, intrinsic heavy quarks, asymmetries, and so on, all sorts of interesting physics. And in the nuclear case, there's also hidden color phenomena too. And I'll show you this one last plot. In fact, when you do the charm distribution in the proton, you find that the charm and anti-charm are different. And that's the intrinsic charm distribution. And there's a big difference between charm and anti-charm. This is from a recent paper using lattice gauge theory. So we have Poincare invariance, causality, light front holography, a mass scale kappa with color confinement, and this beautiful relation to fourplets. So I will stop there. We just conclude. Now I'm happy to take any questions.
Thank you for your nice talk. You gave us a lot of information. And
yeah, I'm afraid. I apologize for doing so much, but
no,
what can I do?
it's very nice actually, because I'm not used to this formalism with holography, but apparently, I mean, you can do very nice prediction because the fit works pretty nice. Is there some quick question to Stanley? Maybe then we can move directly everything to the discussion in the afternoon. We are a bit over the time. I see Christoph wants to ask a question. Please, Christoph.
Hi, Stan. There's Christoph Hannert from Jülich. You lost me somewhere when you showed equations that look basically like two-particle scattering equations, Schrödinger type like. But then you showed observables like the pion vector form factor, where, for instance, the 4-pi channel and the pi omega channel play an important role. And one sees this interplay of overlapping resonances. And you had a curve that went through all the data, but you showed a formula which was like summing Breit-Wiegands with violates unitarity. And here I got completely confused. How much of that observable in E plus E minus going to pi plus pi minus comes straightforwardly from your formalism? And what do you need to put in addition to get those curves that you showed there?
So I should say Guy de Terman is going to give a more detailed talk in a week from today, and he'll talk about this and so on. But basically, on the time-like side, one is computing the resonances that related with the same trajectory as the pion, and there's a constraint on their weights and so on. I don't think there's a violation of unitarity. You'll have to explain that to me. But anyway, we have several papers on developing the time-like pion form factor with the resonances in the time-like domain.
Okay, well, the adding Breit-Wiegands by definition violates unitarity, but this is something we can discuss offline.
Okay,
don't need to do that here.
I need your
talk.
You're right. Thank you, Christoph.
Thank you for your question, Christoph. I'm sorry, but we are really over time. So I would say thanks a lot for the contribution of the second session. And let's go now for the coffee break, 10 minutes, and then we can start the round.
There is connections between what Kobe talked, his approach, and my approach as well. So we should actually work more together, in fact, to see this. You see the important point, though, is that all the spectroscopy is in M squared. That's a feature of light front QCD.